Hello, and welcome to the Purdue BME 305 tutorial on the node voltage method. The node voltage method is an organized method of analyzing a circuit. It's also the method used in solving circuits using SPICE simulators, such as CircuitLab, Multisim, LTSpice, etc. But why do we need a node voltage method? Wouldn't rote KVL and KCL suffice? Well, the answer is yes, but it's important to keep in mind that solving any circuit requires two E equations, where E is the number of elements in the circuit. And this can be a lot of work if our circuit grows larger and larger. So the node voltage is a way to make these calculations efficient. We still have to solve for two E equations, but we can embed KVL implicitly. So KVL is implicitly written, and then KCL and Ohm's law will do the heavy lifting. And we'll see how this works as we go through example problems. A dual to this method is the mesh current, where KCL is implicit and KVL and Ohm's law do the work. But it's important to remember that we're not doing any new physics here. Nothing is really lost. No information is lost. We're still solving 2E equations, but it makes our lives easier because we can implicitly write these equations, and oftentimes we'll reduce the number of calculations that we need to make using this method. So let's look at an example circuit here. So this circuit has two power sources, a voltage and a current source, as well as a parallel combination of resistors and a series resistor. So the overall procedure for the node voltage method is to first assign a reference or a ground node. A reminder, a node is connection points between circuit elements. So we want to look for a reference to which we can reference all the rest of our voltage calculations, which has many connections to as many of the elements as we can in the circuit. So if I'm looking around, this point right here seems like a good connection because there's no elements between connection points here, and both power sources have connections to this point, as well as two of the three resistors. So this seems like a pretty good spot to assign a reference. Once we do that, then we assign the rest of our nodes names or values that we can reference. Then after that, we can solve for the easy node. So if we look at this point right here, this is an easy node to solve because we can look just from inspection that it's going to sit right at 9 volts. And the voltage change is going to happen across this resistor here, which will have a voltage drop between this point and this point. After we do that, we simply write KCL at the remainder of our nodes, keeping Ohm's law in mind. And this is where KVL will be embedded, in that we write KCL, but we reference our KCL in terms of voltages. And I'll demo that here when we solve this circuit. Once we do that, we solve the resulting systems of equations for all the node voltages, and then we just simply solve for any currents that you may want to know using Ohm's law. So let's go ahead and solve this circuit. So, like I had alluded to before, step number one is to assign our ground node. So a good ground node, again, is going to be right here. Now, a reminder, because we have no elements attached across this wire, this is all going to sit at a potential of 0. So we've got our ground assigned. Next, let's assign our nodes. We'll notice something here, that we could assign node values to here and here, but these are going to sit at the same potential because this wire is not going to have any potential drop. Furthermore, we see that we can simplify this circuit by doing a parallel combination of these resistors here. So this we're going to end up assigning as a singular node. So let's go ahead and rewrite the circuit to reflect our equivalent resistance here. So we'll add in our voltage source as normal. And I highly encourage that as you're solving circuits that you're making as many marks on your circuit and your paper as you can. That tends to help out with the thought process and your calculation. So redrawing circuits over and over again, I think, is a good thing. Get our current source. 2 amps. This is going to stay 1 kilo ohm. This resistor, as a parallel combination of 500 ohms and 400 ohms, is going to end up being about 222.22 ohms. So then we can assign a node name here. Let's just call this node number 1 to make our lives easier. Okay, so then number 3, we're going to solve our easy node. So if we wanted to call this node maybe V source, we know that V source is equal to 9 volts. Okay, so step number 4 then is to go ahead and write KCL at that node number 1. So let's go ahead and assign some currents. Now, when you're doing node voltage method, it's important to follow the passive sign convention and take care that we are really noticing where our voltage drops are occurring. And remember, current is going to flow from the positive to the negative. At least that's how we're going to define it here. So we know that this side of the circuit's going to rest at a higher potential than this side, and that's because of this voltage source right here. So we'll assign a positive on this end and a negative on this end, and we will say that the current flows from positive to negative. And so we'll call that current I1. Now let's look here. We know, I forgot to draw my ground sign, but by virtue of this being a reference of 0 volts, we know that this point is going to rest at a higher voltage than this point. So we'll say plus minus here and draw a current here, and we'll call that I2. Now this point, we simply know that the current is going to flow in this direction just due to the arrow of our source here. So we'll call this I source. So a reminder, with KCL, we want to sum the currents entering a node equal to the currents leaving a node. So if we write KCL at node 1, we will have I1 plus IS is equal to I2. Excellent. Now this is where KVL becomes embedded. And the reason is that we see this voltage drop between this point and this point. And that voltage drop is simply the voltage at this point minus the voltage at this point divided by this resistance. And that will get us I1. So we can write I1 is equal to Vs minus V1 over 1 kilo ohm. Is we already know because it's the source here, so we know that's going to be 2 amps. And then likewise, I2 is going to be the voltage at this point minus the voltage at this point divided by this resistor. So that's going to be V1 minus V ground over 222.22 ohms. But check this out. Because we set this reference to this point here, we already know that VG is equal to 0 volts. So we can rewrite this as V1, well, not minus 0, because we would just say V1 over 222.22. And there we go. So the next step then is we'll just go ahead and solve this system of equations. So let's write this out as Vs, which we know is going to be 9 volts, minus V1 over 1K plus 2 is going to equal V1 over 222.22. So check out what's happening here. Normally we would have had to write multiple equations with KCL and KBL to get these values. But we reduced this into a singular equation because we've embedded KVL into our KCL equation, making this a heck of a lot easier. So we can rearrange this. Let's go ahead and write 9 volts minus V1 over 1K minus V1 over 2.22 is equal to minus 2. And then we can carry on as normal, step number 6, and solve out the circuit. And if we do that, we'll find out that V1 is equal to 365.3 volts. And we can always check this by back calculating our KVL and KCL equations within the circuit to verify that all of the currents sum to 0 and all the voltages sum to 0. But that's the general method. And the reason why our circuit simulators use this method is because it's quite efficient to write out these systems of equations. So let's move on to a little bit more of a complicated example. And this is a little bit more complicated because we are now including dependent sources, but we can handle dependent sources just as easily. So let's look at what we have here. So our dependent source is based upon this current here. So that's already been given to us. And what we want to solve for in this, or what I want you to solve for, is find V0. And so V0 is going to be the voltage across this resistor, which also is just the voltage at this node here. So what I'd like you to do is pause this video and, using what we've learned so far, try to solve this circuit for VO. Okay, hopefully you gave this an attempt. Let's begin by assigning our currents. So let's go ahead and assign a current down this way. And we'll call this I0 just because of the V0 here. And then we'll go ahead and call this ID for I-dependent source. So step number 1 of the node voltage method is to assign a ground node. And like I had said in the previous example, we're looking for the place which has as many connections as possible that is uninterrupted. This looks like a pretty good place to be. So let's go ahead and assign our ground node here. Okay, excellent. So the next step is assigning the name of our node voltage here. Let's call it VA. Okay, so now we'll write our KCL at A. Okay, so that's just going to be the currents entering equaling the currents leaving. So we have I delta I delta plus ID equals I0. Okay, so now let's write out our embedded KVLs. So what's I delta going to be? It's simply going to be the voltage at this point minus the voltage at this point divided by this resistance. So we're going to have this is 500 volts, so we'll have 500 minus VA over 5. Okay, ID. So this one we actually don't need to write out any equation with respect to voltage because it is dependent upon this current here. So we know that ID is equal to 5 I delta, which means that we'll end up referencing back to here. We'll see how that makes our lives a little bit easier when we write out this equation. But first, let's write out I0, which again is just going to be the voltage here minus the voltage here. But the voltage here is already set to 0. We've defined that to be 0. So we're looking at the voltage drop from A to 0, meaning that that's just going to be VA divided by 20 ohms. Okay, so let's gather those values into our KVL equation. So 500 minus VA over 5. And I'll go ahead and leave this as 5. I delta for the moment is equal to VA over 20. So we need to get this in terms of VA, but luckily we've got this already here. So so what we can do is sub in for this I delta value here with this. So what that's going to give us is 500 minus VA over 5 plus 5 times 500 minus VA over 5 is equal to VA over 20. All right, and look what happened here again. We simplified this circuit where we'd have to have multiple equations, multiple unknowns. By implicitly writing KVL, we've now got this down to a singular equation that we need to solve. So let's begin hammering this out. So we're going to have 500 minus VA over 5. Make sure you guys can see that. Plus 2500 minus 5 VA over 5. Now you have a couple of choices here. I could have simplified that, but I'm doing this so that I can add these two VA terms. Again, you can solve this any way that you feel is best. And that's going to be equal to VA over 20. So if we bring this over to the other side, then that's going to get us, and combining these two terms, that's going to get us 3000 minus 6 VA over 5 minus VA over 20 is going to equal 0. So a good path to maybe take is to multiply multiply this by 20. That way we can eliminate this 5, and everything will be in a way where you can combine like terms. So let's go ahead and multiply by 20, which is just going to get us 20 times 3000 minus 6 VA over 5 minus VA equals 0. So this goes away, this becomes 4, getting us minus 6 VA minus VA equals, my fault, 24 VA equals 0. Okay, so then this will eventually get us to 25 VA equal to 12,000, and VA is then equal to 480 volts. Now, a reminder, I wanted you all to solve for V0 here, but VA equals V0, so equals VA. And so we've solved the problem using node voltage. Again, we've reduced the amount of work that we really have to do by embedding our KVL into our KCL equations. So let's look at one more sample problem. And this one is going to have multiple nodes that we have to solve for. and it's going to have a little bit of a twist. So again, I want you to pause this video and try to solve this circuit using the rules that we know. Now, what's going to be tricky is how do you deal with this 5-volt source here? So go ahead and ponder this problem, pause it, give it a try, and then come back and we'll see how it's solved. Okay, let's go ahead and start by first of all assigning a ground node, but we'll notice something as we try to assign this ground node in that there's not really a good place to put it. We don't really have a spot that has multiple simultaneous connections, and we certainly, no matter what we try, we certainly can't place it where both voltage sources have one end that is attached to ground. So we really can't win here, but let's just go ahead and assign it to be right here and work from there. Okay, so the next thing we'll do is that we'll solve for, or we'll assign our nodes. So let's call this node A, node B, and node C. So we'll see how all of these nodes will be related to each other here in a second, but we do know if we wanted to solve for the easy nodes, we know that node A is going to sit at a value of 9 volts. We can't say the same for node C up here because of this resistor value, but we'll see what's going to happen here in a second. Okay, so let's just choose a place to place our, or to solve for our first node. Node B seems like a pretty good place to start, so let's just start at node B. So KCL at node B. So to do that, let's go ahead and assign some current values. Again, we want to go with the convention of going from plus to minus. So we see that this side of the resistor is probably going to sit at a higher voltage than this side. So let's go ahead and assign a plus and minus. Again, as long as you're consistent here, the math will sort itself out. But this is how I like to do it. So then we know that because of this ground, that this side is going to sit at a lower voltage than this side. So we'll say plus minus here. And likewise, we'll have, let's just have the current circulating in this direction, pardon me, just to show you that we can go against the convention as long as we're consistent. So we'll say our current goes this direction as well. Again, you could also assign it the other direction and your math will end up working itself out. So this is just to help keep us organized. So let's call the voltage across the 1.5 k ohm resistor as I1, or the current through that, sorry, not the voltage. The current through this resistor, we'll go ahead and call this I3 because I want to call this I2. So now we can write out our KCL equations, remembering that the current entering a node equals the current leaving the node. So let's say that I1 is then equal to I2 plus I3. Okay, so let's start embedding in our KVL into these equations here. So I1's decently easy because we have a voltage A minus a voltage B over this 1.5 k ohm resistor. So I1 is equal to VA minus VB over 1.5 K. Okay, now I3, this one's also going to be relatively easy because we're simply looking at the voltage from B going down to ground. So that's just going to be VB divided by 2K. Okay, and now what about I2? Notice that we've got an interesting little bit of a conundrum here in that the voltage source doesn't dictate our current. The rest of the circuit dictates the current. That's why we say that current is drawn from the source, because there's no equation here that tells us what this voltage source will do with the current. So this is an interesting case that you'll sometimes come across when doing node voltage method, and this is known as a supernode. And this happens, a supernode happens when you have what's known as a floating voltage source. And floating because we don't have either end that is tied to ground. So some people might think that this sinks our ability to do node voltage, but really, just because we're doing node voltage doesn't mean that we can't use some of the other equations. We can't write out another simple KVL equation. Remember, all we have to do is write the number of equations for the number of unknowns that we have. So we can go ahead and use this relationship via KVL up here to write another equation that we can use to solve for our other KCL equation. So let's go ahead and notice that if we were to write a KVL equation here, that this voltage, whatever this node voltage is resting at, is going to be a addition of VB plus the 5-volt source here. And so we got that just by noticing what the voltage drop across between VB and the sources. So we can sort of use this extra equation to exploit this supernode and add in the extra equation that we need. So typically, whenever you encounter a supernode like this, a good strategy to take is just to write another KVL or even another KCL equation, and that will oftentimes solve the floating source problem. So, because we now have this, we can write that the voltage, or sorry, the current through this resistor is simply VC minus VA over 1K. And that's VC because we have the current going in this direction, minus VA, which is where the current is running to, divided by this resistor here. So we can further simplify this by noting what VC really is. Well, it's VB plus 5 volts. So we can say that this current, I2, is equal to BV plus 5V minus VA. Now, what is VA? VA, we already know is it's the easy node to solve for, is just 9 volts. So we can say minus 9 volts divided by 1K. And notice what has just happened. By having this extra equation, we again reduced the solution of the circuit down to having to find a single unknown. Because if we can find VB, then we can also find VC. So again, this is the power. Even when node voltage sometimes doesn't go as well as we had hoped, it still makes our lives relatively efficient in solving these equations. So let's go ahead and solve this out. So let's go back to our KCL at node B. And so that's going to be 9 minus VB over 1.5K. And that's coming from the voltage here minus the voltage here. Or sorry, the voltage here minus the voltage here, because we're going with our current convention, divided by the 1.5 k ohm resistor. Okay, and that will then be equal to VB plus 5 volts minus VA over 1K. So that's again coming from this loop right here. And then we'll just add in the current through this resistor. Oops. which is just going to be VB divided by 2K. So then if we end up solving this equation out, again, this video is running just a little bit longer than I like, so you can solve this out, and if you do that correctly, then VB is going to equal 4.62. Then that would make VC equal to VB plus 5 volts equal to 9.62 volts. And we already know VA is 9 volts. So then we can go back and back calculate Ohm's law and find all of the resulting currents. So this is a particularly interesting example to see that even when things don't look quite right, we can still use node voltage to a very nice effect. So hopefully this tutorial was helpful for practicing and learning about the node voltage method. And as always, if you have any questions regarding this, you can always reach out to me. And with that, I hope you have a nice rest of your day.